present what we did in exploring how we use static code analysis tools for detection of security vulnerabilities. This work was done in collaboration with my graduate student, Andrei Perhinschi, who's here today and is going to co-present with me together. We are both associated with West Virginia University in Morgantown. And the work that I'm presenting here today is, based on the Capability Development Initiative funded by NASA IV&V facility in FY13. And before we start the technical talk, I would like to thank several people from Tomcat and IV&V that did collaborate with us and provided valuable input and feedback on weekly tag-up meetings. These include Keenan Bones, Travis Delson, Roger Harris, Joel Loretta, Jerry Sims, and Chris Williams in an alphabetical order. All of them were really very helpful in what we did. What this is about, we all know that NASA develops, runs, and maintains many systems for which one or more security attributes are important. In some cases, maybe confidentiality, in other integrity or availability or other attributes. Now, which leads to the need to incorporate information assurance and cybersecurity as part of the traditional verification and validation process that deals with software bugs. There is a lot of connection between these two because many of the tags are based on vulnerabilities, which are nothing but software bugs that somebody exploited with a malicious intent. Now, we specifically focus on static code analysis because that is one of the tools that is used widely in the industry, including in IV&V, for verification and validation. The reason being is it's very scalable, so it's done without running the code. Scalable way to do code reviews. Also, the support of tools has increased much in the last decade because these tools evolved from very simple lexical analysis tools 10 years ago to more complex and accurate techniques. However, there is a fundamental problem with static analysis, which is in computer science terminology called undecidable. The problem, which means the problems cannot be solved in such a way that there is a guarantee of a correct solution. Simply, that means that no matter these algorithms and tools can improve, but they can never be correct 100%. In a practical terms, that means that we miss some of the bugs, so they are false negatives, and also often tend to produce a large number of false positives, or part of the code that are believed to be for our purpose vulnerable, but for closer inspection not to be vulnerable. So the goal of this method is to examine the ability of static code analysis tools to detect security vulnerabilities. So we basically only focused on security software bugs that are related to security vulnerabilities. All the others are not considered in the work that we did. Now, the process started with surveying the literature and vendor-provided information in order to cover common languages and other languages more specifically used at NASA, as well as different tools with different capabilities. We ended up with a survey of 15 commercial products and 8 tools that are licensed under some sort of open source license. And within the 6 months that we had, we couldn't explore hands-on all this, but together with NASA IV&V selected 3 tools for detailed evaluation. Just want to make sure here that all of these tools and most of the others that we surveyed require to really to fully use their functionality, require either a build or at least the code to be compiled. Some tools allow to use their functionality without being able to compile the code, but then it's less benefits that one can get. So when we evaluated the performance, we wanted to make it more quantitative in the sense we have an idea of how much assurance one can have from using static code analysis for detecting security vulnerabilities, and therefore two approaches. One of the approaches was to use micro benchmarking test suite that is exists for C, C++, and Java. Um, and the advantage of that approach is this is a synthetically generated approach that has a large number of testing cases, and because its benchmarks allow us to have a common ground for comparing the tools. However, because it is synthetically generated and consists of small programs, we also have a second approach using real programs of reasonable size with known locations of vulnerabilities to evaluate the tools. So we will now see the more details and of how the relation is based on Juliet test suite, which is the micro benchmarking um, test suite, and Andrei will tell you a little bit more detail.
All right. So Juliet is a micro-benchmark suite developed by the NSA for the specific reason of targeting of testing static analysis tools. It is based on automated declaration nomenclature, which is a system of classifying design vulnerabilities. For example, CWE1 stack-based multi-road flow. There's a different one for null pointer dereference, etc. As Dr. said, parts of Juliet. There's a C++ test suite, which consists of 119 CWEs with about 60,000 test cases. And the Java one, 13 CWEs, about 44,000 test cases. Now, these many thousands of test cases, each of them, they're little tiny programs. They can how they can run individually. These are our inputs to our free static analysis tools. Each one of these test cases only consists or only one batch function or method in Java that contains all the constructs. Only one. Then there are four more constructs as well, and this is how we use this in an automated way to compute the number of positives and negatives and so on. Everything you guys see in this presentation is based on the CWEs that are common among all three of our tools. For C and C++, we have 22 common CWEs, which comprise about 1,000 test cases. For Java, we have 18 common CWEs, much as test cases 7,500. Tools that we have listed have support for many more CWEs. Among those two, there's 90 common C, C++ CWEs, and 107 for Java. We don't present the results here as they are very similar to the ones for the common CWEs. So how do we do our automatic analysis here? Of course, the first thing we have to do is run each tool over the Juliet test suite. In order to compute our confusion matrix automatically, we have to take each tool's output and convert it to a common format so we can automate everything. I decided to use simple text format files for all of our results. The other thing that we have to do before we actually compute the confusion matrix is to, for each CWE, we have to parse the directory, the source code directory, and the source code itself. So we need a list of every test case. For every test case, the list function spans inside, so we can count false negatives, and positives, stuff like that. With this information, we compute the confusion matrix, and I think Dr. Joshua is going to talk a little bit more about that.
Basically, Andrei wrote a couple of scripts in Python that does so automatically. However, otherwise, 100,000 test cases machine learning use typically a confusion matrix to evaluate how do different methods do. So here, as I said, we only account for vulnerabilities. So actual vulnerability that exists in this test, test cases can be reported as vulnerability here, which means that it's true positive, or the tool can miss it, which is a false negative. That's of course undesirable event. Then the uh, no a good function that doesn't have a vulnerability in it can be reported as vulnerability, which is false positive. We want to have less of those because it's less manual inspection, or can is not reported, which is true negative, and this is the desirable event. We use a couple of metrics to do evaluation. Accuracy is one of those, which is the overall how good the classification is. This is all the true negatives and true positives versus all cases. The more interesting are the next two. The probability of detecting a vulnerability, which sometimes is also called recall, is what is our probability or percentage of true vulnerabilities out of all that the tool can detect. While the probability of not classifying a good function as a bad function, which is false alarm, is given by the false positives over the all no vulnerability. Now, ideally, a good tool will have as high as possible close to one probability of detection and as low as possible close to zero false alarm. Now, because these two are important and we need to have some balance between those, we also use geometric balance here that gives us distance from that ideal 0, 1 point of how far it is. And the larger the balance is, the better we are. And this is going to become more obvious when we saw the one-on-one square of false positive, false alarm, and recall. So these are all produced for C++ and Java automatically by the programs that we develop, and here are the results. The accuracy is the overall how good the classification is for the common C++ CWEs. On this axis, you see these are different CWEs. On y-axis is the accuracy, and the closer to 1, the better off we are. We also represent here the ranges, averages, and medians. And you can see both by the bar graph and these values, then the tools have similar performance, not very good, some over 50%, some little bit over, with the two each, which is one in green, performing slightly better. If you wonder why the 2A, 2B, 2C, the licenses of tools are fairly restrictive and do not allow disclosing results, so that's why we are disclosing the sanitized results. But overall, there's not big difference, and one of the tools does slightly better. Then you look at the recall. This is very important because it gives you the probability of detection of vulnerability. You want to be as close as possible to 1. The interesting thing here is that for some vulnerabilities like 561, which is that code, all three tools were able to detect 50% of the CWEs. But for some, we see combinations of two tools detecting it, or for others, only one tool detecting it. The fact that all three tools detect any of the vulnerabilities that are listed here seems to be very important. So 197, 391, 478, these are CWEs standard that's maintained by V&V, and these are standard CWEs. That means that out of the three tools, none has detected any of the best functions. This also gives us an idea that accuracy is not a very good metric, because accuracy, as you can see on the previous graph, because gives an overall classification, is fairly good, even for the cases when the tools miss the bad function, because they successfully classify the good function. Now, the false alarm rate is the one that we here, uh, tools differ, and in this case, tool C, this is the green part, are has a noticeably lower falsification rate than tools A and B. So, which means that there is less cases to be examined for whether they are vulnerabilities or not. Now, the balance was the metric that takes into account both the recalls, probability of detection, and the false alarm rates, trying to see how far we are from our ideal point of zero false alarm and one probability of detection. We see here for many CWEs the balance is around 30%, which indicates not very good overall performance. And we also see that the 2C performs something somewhat better. Now, these are the graphs here, which are called rock squares. For each of the three tools, 2A, 2B, and 2C. And we probably cannot see the numbers, but we wanted to have them next to each other so we can compare. On x-axis, we have the probability of false alarm. On y-axis, we have the probability of detection. And the closer we get to these points here, 0, 1, the better the tool is. That means a lot of detection, very few false alarms. Now, common to all is we see not many points close to this 0, 1. Also, C here has noticeably lower false alarm rate. You see there's less points with false alarm rate greater than 0 than the other two tools. And also this here is multiple, for each tool there is multiple CWEs that the tool misses altogether. So they don't report any of the bad functions associated with that tool. So this really the biggest best amount is using how far you are from this ideal point, and the higher that is, the better off we are. So this seems to be fairly consistent with the results of one of the previous presentations where some people analysis tools were used for regular bugs, not for security-related vulnerability. Now, we also for Java. Now these are different test suites because Java has some. There are some common vulnerabilities in Java. Java has specific like C++ have pointer related stuff that doesn't appear in Java and so on and so forth. So the results are fairly consistent, a couple of differences that I'm going to try to point out here. For the accuracy case Java CWE, we see a little bit more variability. We also see that in some cases like here, let's say CW581 has 100% accuracy, which means all bad and good functions have been successfully classified. And we also see that 2C seems to slightly outperform the others, but there is still not very significant difference. Now in the case of Java, there is a couple of points, a couple of different points. We also see more variability. We also see more CWEs where we have 100 probability of detection. There is less CWEs that are missed, only 2, 486 and 489, but Java has less test cases also. And way up and down the other two here, this is the one in yellow, tends to have better recall for Java. So it tends to catch more Java related CWE. Probability of false alarm again similar to the case of C, C++, and the 2C consistently, which is the green bar, you see it's missing here, consistently has smaller false alarm probability than the other two. If we look at the balance, again, quite a few around 30%, we have several that are higher. And it seems that A and C, which are yellow and green bars here, slightly outperform the others. So all this can also be obvious here by the average and the medians that are given. Just in the interest of time, I'm not going through those. So basically, on the rock squares, again, for 2A, 2B, and tool C, we have false positive on x-axis and then recall on y-axis, very similar. There is a little bit less difference in the false alarm rate. C is still better, but not that much. We also see several more points, but not too many around our ideal 0, 1 point. And we also see CWEs in 0, 0, which means each of the tools misses some of them all together. Now, of course, not all vulnerabilities are in tools that are more critical than the other. One way to look at the critical vulnerabilities is to look at the some top 25 most dangerous software errors, which is published on yearly basis. So we looked at those, and just a comment here, the Juliet test cases don't cover all because some CWEs are design oriented, so they don't translate in code very well. From those that were in the common set that we are presenting here, observations are not much different than for the others. The tools, it's again a mixed bag, and in cases like, for example, CWE78, it's operating system comment injection. Tool A has highest recall of 54, so detects 54% of vulnerabilities, but also has very high false positive rate. The other two tools, B and C, performed poorly. They have recall values of only 4 and 0%. So one can go through all these in details, but the main point is then we again see similar performance as for the rest of those. So in the interest of time, I'm going to skip those and pass it to Andrei again to tell you a little bit more on the evaluation based on real programs. And I cannot resist to tell you my usual joke that I tell to students in class that are much younger than me, that I'm not all computers develop very fast. So most of us are working with big listings of programs that you don't see as much around anymore. Andrei here will tell you a little bit more details about testing that we did, which was done now manually on a real software much larger than the Juliet testing.
Okay, so real quick, the reason we decided to also test some real software is because we were worried that our static analysis tools would behave differently than with the Juliet test suite, which again is automatically generated. All the test cases are generated by computer. Decided on 3 open source software applications, Gzip, Tomcat, and Tomcat. One old version of each one with known vulnerabilities, known physical location and code, line number, function name, etc. And a recent version for each one with those same vulnerabilities fixed. We had a total of 4 known vulnerabilities. So the first one, Gzip. It's the tiniest one we had. It's written in C, and we have 4 vulnerabilities that we reviewed for it. The results, as you can see here, tools A and C found 1 out of 4 known vulnerabilities. Tool B found none. In the fixed version, tools A and C had false positives in terms of they found the same vulnerabilities even though they were supposed to be fixed. Also, note here that false positives only refers to the vulnerabilities that we knew of. As you can see, there's many more warnings, so some of those might actually be false positives or true negatives, etc. The second real piece of code we used was Dovecot. It's an IMAP POP3 server for Unix machines. It's also written in C, and it's about 300,000 lines of code containing 8 known vulnerabilities. None of the 3 tools found any of the 8 vulnerabilities for Dovecot, and none of them found them in the fixed version, which is good. The largest piece of software, the last one, was Tomcat. It's a open source Java servlet and Java server pages implementation written in Java. It's about 5 million lines of code, and it contains 32 known vulnerabilities. Now, because it's so much bigger, a lot of the vulnerabilities, most of them actually, are split amongst either several files or multiple locations within the same file, which is really unlike the smaller applications. Usually, the vulnerabilities consisted of just one bad line of code or a tiny block. So we consider a true positive in this case if at least one of the files and or locations were matched by one of the tools. Now the results of Tomcat are, as you see here, tool A performed the best, 7 out of 32. Vulnerabilities detected, C and B in that order. There is also a couple of false positives here, only 2 for tool A and 1 for tool C. And I think that's it for me. I think Dr. Goseva is going to give us some conclusion points.
Okay. I would like to conclude with a couple of high-level remarks. First, none of the three tools produce very good results, which is very high probability of detection and a low probability of false alarm. Tool C appeared to have smallest false alarm rate based on the Juliet test cases, 5% for C, C++, and 7 for C++, and 5 for Java. We saw that some CWEs were detected by all tools, others by combination of 2 or only 1, but all tools also missed, all 3 tools missed some CWEs. The results of evaluation of the larger programs confirmed what we saw for the smaller benchmarking test cases. Basically, they have high false negative rates, miss quite a lot of CWEs, and the 2A also performs slightly better for Java than the other two. The bottom line is static code analysis tools provide some support for vulnerability detection, especially when they are used with the tool support of all kinds of advices of how you fix it, how you remove it, how you avoid it. But they certainly do not provide what NASA may care about is assurance that if you use static code analysis tools, your software is going to be free of vulnerabilities. Other complementary techniques such as penetration testing have to be added to the spectrum of techniques used to really provide assurance. A little bit time left to answer any questions that you have before the break. I wouldn't be that strong because the difference wasn't very big whenever it existed. And it seems that the recall, the probability of detection of 2A was better for C, C++, and for 2C, and for Java was 2A. C consistently has smallest false alarm. But the differences are not really very big or significant to really say, yes, this is the winner. So, oh yeah, yeah, sure. We are with computer science and electrical engineering. Any other questions? Against what? Did we look at Firefox?
We never considered Firefox per se, but I can tell you right now, right off the bat, Firefox is probably several million lines of code. It was kind of a fluke that we even decided to use Tomcat. We weren't really going to use it, but we wanted to use a Java application as well as a couple C, C++ ones, and that was the only one where we could really find locations in the source code for vulnerabilities. We didn't look at Firefox Snow, but we weren't really trying to use to run really large pieces of software through these tools either. So that's
Tomcat was large though. It was
almost
like 5 million. Oh, there is a restriction on what you can use for evaluation. The evaluation with real programs was done manually, and in order to be able to say what is false negative, what the tools are missing, you have to know the exact location of the vulnerability, and then look at the reports of the tool and see what they are reporting. So that is very hard because open source software like Firefox, I haven't checked exactly, may actually have a bug tracker system that says there is a bug, but oftentimes you don't know where the fix was, You may know the file level, but not necessarily the location. So and we only have 6 months to do this. So we restricted to 3 of a different size, one of which is Java CWES, in order to get to look at something that's with reasonable size. We do agree, though, other software. We also try to get some NASA software, but we weren't successful to find software in which the vulnerabilities were known, because people may have known and fixed them, but nobody kept track. So that was the restriction. But our main idea was, when the program is larger, there is much more than just a small snippet of code that can actually make the task of static analysis much harder, and we just wanted to see how they do. Results were fairly consistent. So.
Thank you. If you want to go ahead over to the breakout session, we'll get ready for the next presentation.